Hello chemists and welcome to this lesson on carboxylic acids. Now before we begin, I'd like you to answer these starter questions recapping on what we studied on alcohols last week. So please have a go at these and then come back to check your answers. So the functional group that alcohols have is OH, and we call this the hydroxyl functional group, but it's fine if you just write it as OH like that. Always showing the bond between the oxygen and the hydrogen there, that's important. Okay, so the names of the two methods of producing ethanol are, you should have got fermentation of glucose, which uses yeast, or you could have gone for hydration of ethene using steam. Now remember with that glucose comes from sugarcane, that's its raw material, so plants, so it's renewable, key advantage, whereas ethene comes from crude oil, so that's a disadvantage because crude oil is a non-renewable resource. Okay, next up, if ethanol is produced for use as a biofuel and it comes from sugarcane, why is it carbon neutral? Well, remember that a fuel that comes from a plant, when you burn it or during the production process, it's going to release a certain amount of CO2, and that's the same amount of CO2 released that was originally absorbed by it when it was a plant photosynthesizing. So same amount of CO2 in, same amount of CO2 out. Okay, right, let's begin then. So we're looking today at carboxylic acids, and they're part of a homologous series, which means to differ by one carbon and two hydrogens, so CH2, and they all include the COOH functional group. Okay, so I've got an example here of ethanoic acid, and you can see that it's eth or ethanoic because it's got two carbon atoms, so it gets that prefix, and the anoic acid part of it, the suffix, comes from the fact that it has this COOH group. So let's have a look for that in the structure. It's here. Okay, so you've got the C, double bond O, single bond O, and then to the H, and we abbreviate that as COOH, just like that there. Now, it's really important when we're constructing, naming or drawing the carboxylic acids that we do account for the carbon within the COOH group. So, for example, this is methanoic acid because it only has one carbon. This one here would be ethanoic acid because it's got two carbons. But a lot of people might get a little bit confused because they'll only count the carbon here, but you've also got to count the carbon within the carboxylic acid functional group there. So that is ethanoic acid. Next up we would have propanoic acid. There's the carboxylic acid functional group. 1, 2, 3 carbons as you can see. And then we've got butanoic acid there with its functional group and 4 carbons overall. So we have the same prefixes that we're used to based off the number of carbon atoms, but our suffix now is anoic acid. And you can see the way we write the formula is much like we did for alcohols, in the fact that we write the functional group in its formula very clearly, and then we just abbreviate the rest of the structure. So it probably makes most sense with one like propanoic acid here. You can see we've got the carboxylic acid functional group, and then we've just abbreviated the chunk that's bonded onto that, C2H5, like that. Okay, so let's have a little look at how carboxylic acids are made. So to begin with, what you need to know is that what we can do is oxidize alcohols. Okay, so if you take the alcohols that we looked at previously, if they undergo this process of oxidation, the gain of oxygen, using something called an oxidizing agent, then they're going to turn into carboxylic acids. Now this chemical, the oxidizing agent, we represent in equations using O in square brackets. Okay, so here's an example using displayed formulae for the organic compounds. They're called displayed formulae because we show the bonds, we display all of the bonds in the compounds. You can see here we've got ethanol, and we're reacting it with an oxidizing agent, and we need 2 of them. I'll explain why in a moment. And this will produce ethanoic acid, the carboxylic acid, and it will also produce water there as a byproduct. Now let's have a little look at why we need 2 of the oxidizing agent. Well, remember that the definition of oxidation is the gain of oxygen. Now, if we look at our compound over here, let's have a look at this carbon, the second carbon. See the second carbon on both our reactant and our product. Well, you can see that this carbon here has gained oxygen. Look, we've got this double bonded O on this carbon here that wasn't there before. Now, in order to get that oxygen onto it, we had to remove 2 hydrogens. Okay, so there's our first oxygen out of the 2 that are coming from the oxidizing agent. Now, this structure hasn't gained any more oxygens than that because this one was already in the reactant. But if we are to remove these two hydrogens to make the byproduct, which is water, one of the oxygens needs to go in to make the water there. So the second O of the 2O for the oxidising agent goes into water, so that can be formed. So one oxygen for forming your product, double bonding that oxygen, and the other oxygen's there to be able to strip those hydrogens off to form your water byproduct. So this is an example of oxidation, as I said, because it's the gain of oxygen with respect to our compound here. It's gained oxygen in being converted from an alcohol to a carboxylic acid. Okay, so we've got some questions now on carboxylic acids. There's quite a few of these, not just the ones on this slide. So if you could work your way through all the questions on your answer template and then come back to check your answers. Okay, so the functional group that all carboxylic acids have is the COOH functional group. You can just write it like that, or you can draw it like the C double bond O, OH, like that. Next up, we're asked to name the following carboxylic acids, and always remember to include, when you count the number of carbons for the prefix, the carbon that is part of the carboxylic acid functional group. So this one only has one overall, so it gets the prefix meth, and anoic acid is the suffix, so we've got methanoic acid here. Next one's got 2 carbons overall, so it's ethanoic acid. This one's got 3 carbons overall, so we've got propanoic acid, and this one here with 4 is butanoic acid. If we were to have 5, it would be pentanoic, 6 hexanoic, 7 heptanoic, 8 octanoic, 9 nonanoic, and 10 decanoic acids. Okay, the name of the method that changes an alcohol into a carboxylic acid is of course called oxidation, the gain of oxygen there, where we would use our oxidising agent represented with O in square brackets. Okay, so next up we were asked to complete each reaction scheme, and I thought it'd be important to highlight actually that all of these equations or word equations below are still referring to these particular diagrams. They're just different ways of representing the same thing. So have a look at this to begin with. We've got methanol here. So this is an alcohol. So undergoing oxidation, this one would turn into methanoic acid. So what we need to do is on the carbon that's on the OH, so the carbon that's got the OH bonded to it, we need to add a double bonded oxygen and remove 2 of the hydrogens. So our structure should look like this. So this carbon here, the one that's got the OH bonded to it originally, I'm going to add a double bonded O and I'm going to remove that hydrogen and that hydrogen there. I'll leave any other hydrogens if it has them intact. Okay, now the name of this one here was coming next. Oh, sorry, the formula of this one here was coming next because this is a symbol equation here. So the formula of methanol, which is this starting material, remember we always abbreviate this part and then put OH on the end. So we should have got CH3OH. Now finally, we're asked to name whatever this product is over here. So we've got its displayed formula, its formula, so asked to give its name now. So methanol will oxidise into methanoic acid. Okay, next one then. So we've got to work out what would oxidise into this structure here. So we've kind of got to do what we previously did in reverse. So this carbon here, the one with the OH bonded to it, this is the carboxylic acid here, by the way. This wouldn't have had that double bonded oxygen and it would have had 2 hydrogens on it. So let's go back and affect that change. You would get this structure here, which is of course ethanol. You could have worked it out the other way just by drawing ethanol or drawing that as well, of course. Next up, we're asked to write a formula for this structure here. So I've got CH3COOH. So we should have written that there, just like that. And then finally, we've got to name it. So 2 carbons, carboxylic acid functional group. We're looking here at ethanoic acid. Again, kind of word association, you could have worked out that ethanol goes to ethanoic acid when reacted with an oxidising agent. So lots of different thoughts in terms of our logic in the way that we can get to the same answers. Okay, C next. So this time there's a missing group on all of them. It's the same for all of them. So remember to carry out these changes where we're going from alcohols to carboxylic acids, we need to use an oxidising agent. And we represent that oxidising agent with O in square brackets. And remember that we need 2 of them. One of the oxygens goes onto the structure to form the double bonded oxygen, and the other oxygen, remember of course, so this answers our other question, goes into the byproduct of water. Now in a simple equation, these 2 are going to be exactly the same, so we should have got that there. And then finally we've got to name them. So whenever we see O in square brackets, we're talking about an oxidising agent, and H2O of course is water. Okay, so a little bit more challenging this time. So you've got to work your way to the bottom and then see what we're talking about. So this first box here would have been butanol. So that would have 4 carbons and an O to H group on the end because it's an alcohol because it ends in ol. So we should have got this structure here. 1, 2, 3, 4 for bute and ol for the OH group on there. Now butanol will oxidise into butanoic acid. So we've got to do something that's 4 carbons long, but the 4th carbon is part of that COOH group. Okay, so we're going to have 1, 2, 3, 4, where the 4th carbon C double bond O, O to H to make it butanoic acid like that. So next up we've got to give formulae for both our butanol and our butanoic acid. So butanol, what we're going to do is abbreviate this whole structure and then slap OH on the end of it. So I've got C4 and it looks like H9 there. So I'm going to write that C4H9OH. And again for the carboxylic acid, what I'm going to do is abbreviate the whole bit up until the functional group. So over here our functional group is OH, which is why it just got bolted onto the end, whereas with our carboxylic acids the functional group is our COOH. So we should get this, which is C3H7COOH, like that. Okay. So now what we're going to do is compare strong acids versus weak acids. And you will have looked at this before in Unit 4, Chemical Changes, when we looked at acids and bases and neutralisation and things like that. Now, one of the key things to remember about acids is that they can ionise when they go into aqueous solution. When they ionise, if we class this whole molecule that you see here, so this A- and this H+, as a whole molecule of the acid, and we've got 3 molecules of that particular acid here. Now, when they ionise, what they do is they release H+, or hydrogen ions, into solution, and that's fundamentally what makes them acidic. That's what all acids have in common, the ability to release H+ hydrogen ions. Now, in a strong acid, they fully ionise, which basically means that every single acid molecule breaks up and releases its H+ ions, a bit like this, right? So that one's released its H+ ion, that molecule's released its H+ ion, that molecule's released its H+ ion. So if you were to look at every single molecule of a strong acid, it will have ionised and released its H+ ions. So you can see here we had 3 molecules of acid and we've ended up with three molecules essentially of H+. So it's fully ionised. Every single one of them has released an H+ ion. Now, what this does is it results in quite a high H+ ion concentration because we've got 3 of them and we had 3 moles of acid. Now, that results in a low pH, remember, that's where it's a little bit confusing. So if you've got a strong acid, you'll have lots of H+ ions, which means a low pH, because a low pH means very acidic. And that'll be anywhere between 0 and 3, approximately. Now, we've got a weak acid over here, and just to mention, if I was to take this back quickly like this, the concentration of this strong acid is exactly the same as the concentration of this weak acid. I've got 3 molecules of my strong acid and 3 molecules of my weak acid. Now, if I was to go ahead and look at the weak acid now though, to be called a weak acid, you only partially ionise. Now what this means is that only some of the molecules are actually going to split up and release their H+ ions. So that results in a lower concentration of H+. And if you've got fewer H+ ions, then you're not going to be as acidic. So you're going to have a higher pH, probably in the range of about 4 to 6. So although these 2 acids, the strong acid and the weak acid, originally had the same concentration of 3 moles of acid, let's say, per cubic decimetre, the actual number of H+ ions that's in solution is different. This one released 3 H+ ions, whereas this one only released 1. And that's because weak acids only partially ionise, whereas strong acids fully ionise. Now, if we refer this to our carboxylic acids now, well, carboxylic acids are an example of weak acids because they're only going to partially ionise in aqueous solution. So if I had 3 molecules of, this would be ethanoic acid, right? Because it's got 2 carbons on it. If I had 3 molecules of the carboxylic acid, then maybe only one of them would actually ionise. Okay, so we'd end up with quite a low H+ ion concentration. So you can see here one of the molecules is ionised to release H+, but the other molecules have stayed intact. So that's an example of a weak acid only partially ionising there. So carboxylic acids don't tend to have low pHs like strong acids would. They have pHs that are closer to neutral, so 4 to 6, getting closer to that 7. So they're not as strong, they're not as corrosive, they're not gonna be as good at necessarily neutralising things. So let's have a look though now at an example of a carboxylic acid neutralising another substance, carbonates. Remember, carbonates are an example of an insoluble base, a base that does not dissolve in water, but it will dissolve in acid. And carboxylic acids are going to react with carbonates much in the same way that any acid would. And this is going to be an example of a neutralisation reaction. Now remember, whenever we react a carboxylic acid with a carbonate, a metal carbonate, then what happens is it neutralises the carbonate to make a soluble salt, so a salt that's dissolved in water. It'll also make water as a byproduct of neutralisation, but because we've reacted a carbonate, something that's a CO3, you're also going to get carbon dioxide gas come off of that, which you're going to observe in the form of effervescence. Okay? So remember that they will produce carbon dioxide, water and a salt, and it's an example of neutralisation. And a word equation for this might be something like ethanoic acid plus calcium carbonate goes to make calcium ethanoate plus water plus carbon dioxide. Now the main facts you need to know, you're going to observe effervescence of CO2, and that carbonate that reacted is going to dissolve as it reacts, as long as there's acid there to neutralise it. Okay, so some final questions now. Please pause the video and then come back for your answers. So, strong acids are going to fully ionise in solution, which results in a higher H+ ion concentration and therefore a low pH. Whereas weak acids only partially ionise in solution, which results in a lower H+ ion concentration and therefore a higher pH. The kind of acids that carboxylic acids are, and an explanation for this, is that they are weak acids because they only partially ionise. And finally, we've got to describe what we would observe when ethanoic acid reacts with calcium carbonate. Well, the first thing we're going to observe pretty much straight away is the effervescence of carbon dioxide gas. So you're going to see bubbles, which of course you could test by bubbling it through lime water, which is the test for carbon dioxide, which would turn from colourless to cloudy. And the second observation you're going to have is that the metal carbonate, so calcium carbonate in this case, would actually dissolve as it's being neutralised by the acid. Okay, thanks very much for watching, guys. I hope you found that one clear. That was carboxylic acids. Next week what we're going to do is have a look at how you can actually then take a carboxylic acid and an alcohol and react those two to form something called an ester. So if you want to move ahead and look up esters, then please do be my guest. Have a look at what we're studying next. Thanks very much for watching. See you next week.